All right. So today I'm going to continue where I left off last time. So we are still going to look at object-oriented programming. And today I was last lecture I stopped at this concept of an abstract class. Okay. So you can in Scala you can define abstract classes like abstract class A, and you can define some members in this class. You can define some member functions. Something like that. You can also define member functions, but you can leave them unimplemented. And that's what makes it abstract. The reason it's abstract is because there are members here which are uninitialized. So there are uninitialized fields in the class. And there are undefined members. And this makes it nice. This makes it a way to specify an interface. Typically, that's how abstract classes are used, to specify an interface and hide the implementation details. It's yet another mechanism for encapsulation. It's yet another way by which you can hide some implementation details and just expose some interface that you want people to use. And of course, if you have an abstract class, the reason you have abstract classes is you want to derive from these abstract classes. And you can say class B, and you can say override val I colon int, override val j colon string, extends A, and then you would say def bar or override def bar x colon int equals. Okay, so you want to the one reason you can make class B non-abstract is you better define the things that have not been defined. So if you want a regular class which is a non-abstract class, so if you want a non-abstract class to derive from an abstract class, you better initialize or implement everything that needs to be initialized or implemented. And here that means that you provide a way for me to initialize I and j. As an example, here I have given you a way to initialize I and j by making them the parameters of the class. So when I create a new instance of B, I have to tell you what I is, and I have to tell you what j is. That's one way to initialize it. Another way to initialize it is you could do something like this. You could say, I'm initializing I through a class parameter and initializing j by setting it to something like I.toString or something like that. Okay, and here, let's say bar just returns I plus x. So this is one, these are two ways by which you can do it. You can either initialize a field by making it a class parameter, or you can put it inside the class and initialize it as the part of the initialization of the class. On the other hand, if I fail to initialize j, what do you think will happen? So if I forgot to initialize j, or I forgot about j, what do you think will happen? Yes, so you're going to get an error, right? So it's going to say class B needs to be abstract. When you get such an error, what's happening is, so either make it abstract, or it's telling you exactly what's not been defined. Since the value j in class A of type string is not defined, so you can define it. Since value j is not being defined, I just defined it. Oh, even this doesn't. Oh wait, can mute the rest of the class. Is there? I can't hear anyone. Can you hear something?
I have one drink.
Okay.
Yeah.
Let's do that. Hold on. So I need to mute all participants. Let's see how I do that. Okay. Interestingly enough, I can't hear anything, but That may be because my volume's muted. Just a second. Let's do this. Yeah.
Wow, it's really you. Thanks, but I don't know.
Matthew Wu. All right. Better now? All right. Thanks, everyone. Yeah, for some reason I couldn't hear it. All right. Okay, so let's keep on going on. Can anyone explain why this code gives an error now? Hopefully the screen's back. Can anyone explain why this code gives an error? Okay, because even though I have declared J, I haven't defined it. So I have to define it to something. I can define it to a constant, or I can define it to a toString. Everyone okay so far? All right, so this is where we ended up last time. Now it turns out Scala has a different thing called a trait. Okay, a trait is in Scala is very much like an abstract class. So you can define traits, and typically traits are like you define a trait called summable. Okay, and you would say in that trait I have to say, okay, let me define a function called add. Okay, and I can say x colon int, y colon int, colon int. So this is an example of a trait. All right, and a trait is essentially an abstract class, and it can have the same things that an abstract class has. So it can have member fields. It can have member fields. It can have functions. It can have things that you define. And it can have fields that you define. It can have methods that you define. Something like that. So you can have some methods where you make a definition, you provide a definition, exactly like in an abstract class. The only difference with a trait is a trait cannot have class parameters. A trait is not the same as a class. You cannot have class parameters in a trait. All right. So a trait defines some uninitialized fields, some uninitialized fields, uninitialized methods, undefined methods. Okay, but a trait is not the same as a class in the sense that here's what you can do with a trait. You can, just like you can inherit a class, there is a concept in Scala called a mixin. So what is the effective difference between class parameters and fields of data in a trait? So first of all, so the main difference, so let me go back to an abstract class, right, or a class. A class can have class parameters like this. And these are things where you define them when you call the constructor of the class. All right, so you can create a new instance of B by saying new B 25, in which case this 25 becomes the value of I, and the class gets instantiated that way. Whereas you can have fields inside the class which are not class parameters. They are also initialized when you create a new instance of the class, but they are initialized indirectly by setting them to whatever you initialize them to. Okay, so that's the difference between a class parameter like that and a field of the class like that. A class parameter is also a field in the sense that you do have the notion of, let's say, val b equals new b. You can say b.i. So I is a part of class b, but it's even better. It's a class parameter. Okay, you can say b.i and b.j. They do make sense, and b.bar, and because it extends from a, you do have b.foo. You do have all of those, right? So it's a it's not like a really different thing, a class parameter and a field. It's just a class parameter is a field that has been exposed to the user. So that when they instantiate your class, they can set it to a value. Whereas in a trait, you cannot have class parameters. All right, a trait cannot be a class parameters because you can never define a trait. You can never create a new summable. That is not possible. Okay, the only things you can do to a trait is you can inherit from a trait, and this is exactly where a trait is treated exactly like an abstract class. Or you can do something called a mix-in of a trait. And here, a trait is treated like some helpful methods or definitions that can be added to a class. Okay, so I'm going to talk about both. So a trait can be treated exactly like an abstract class. So what does that mean? So that means this. So a trait, you can define a class, let's say class B, and you can extend, just like you can inherit from abstract class, you can inherit from a trait. So you can say class B extends summable. Here summable is a trait. Now, of course, your job here is to then override and define J, because you have to define J, you have to define I, and so on. So you can define J, and then you can define I somehow, either as a class parameter, or you can define it as a field in the class, something like that. All right, and you have to define add. So you have to say override def add. You have to do this. Something like that. So you have to define these things. You don't have to define X or sum up because they are already defined. You could override them if you didn't like them, but they are already defined. And so this is an example of using a trait. This is an example of using a trait exactly like an abstract class. Okay, so that's one way to do it. The other way to do it is something called a mix-in composition. So something called a mix-in composition. So what's a mix-in composition? So remember, in Scala, you cannot have multiple inheritance. So what does that mean? So I cannot have a class that inherits from both from, let's say, B and from C. So I cannot say, so let's use different names. Let's call this, B, something like that, so that I can show you this. So I cannot have a class, like I cannot say class C extends B and extends summable or something like that. I cannot have multiple inheritance, even though in other languages you can have multiple inheritance. Like in C++, you can have multiple inheritance. In Scala, you cannot have multiple inheritance. So multiple inheritance is not allowed in Scala. But suppose I wanted to inherit from both classes here. I wanted to inherit from both from summable and B. All right. How do I do that? So I would request you to keep all the logistical questions at the beginning of the class. When I'm trying to explain the difference between a trait and an abstract class, I would rather not hear about whether project 3 will replace the final. Please ask me these questions after class. All right. So where was I? So how do I do multiple inheritance in Scala? So in Scala, traits allow you to do some form of multiple inheritance. All right. So what does that mean? I can actually define classes. So I can define a class, let's call it C, which extends, let's say it extends A. So it inherits from this abstract class A. And you can also say with summable. So what you can do in Scala is you can inherit from a class. You can inherit from a class and you can do what is called a mix-in with traits. Okay, so the idea here is you are not allowed to do multiple inheritance, but you can do the following. You can inherit from a class, and you can do what is called a mix-in, where a mix-in uses a keyword called with, and you can say summable. So the idea here is then B can be upcast to a class of type A, but B will also at the same time, or C at the same time, will also get all these fields from summable. Is that okay? So you can do multiple inheritance in this strange way where you can inherit from a class, but you can also have the idea that you can mix in with a trait. Now, the interesting thing is you cannot take C and upcast it. You can take C and upcast it to A, but you cannot take C and upcast it to something like a summable. So you cannot do this. That makes no sense. So you can't upcast C to a summable, but you can definitely upcast C to an A. Okay, so there is this notion called a mix-in, and the mix-in idea is exactly like multiple inheritance, except that it changes some of the details of how you can upcast. Is that okay? So let me illustrate some examples of how we do this. All right. So let me start by illustrating some examples of how we do this. Yes, we can have multiple width. You can have multiple mix-ins for multiple classes. So let me give you an example. All right. So let's start with a basic class. Let's start with a basic class. Let's say animal. All right. So we'll start with an abstract class called animal. Okay. And let's say we have its genus. Let's say we have its species. And let's say we have the sound that it makes. Okay, what sound does it make? And let's just leave it at that. So let's say we are interested in creating something like this. Okay, so we define an abstract class called animal, and now let's say we want to derive from animal. So you can always say class bird extends animal. Okay, and now what you have to do is so let's say class hummingbird extends from animal. I'm not a biologist, but you might have to say override val genus is humming, whatever the genus and the species of hummingbird is. I don't know, but bird or hummingus birdus, and then you say defined sound, because the genus and species have to be in Latin, and you say defined sound is too high pitched to hear. So you can create a class hierarchy this way. So you can define a class, let's say frog extends animal, and you can say override val genus string. So you can write all of these things. Okay, this I remember. So you can write stuff like this, and you can say def sound string equals ribbit. All right, so you can have this, right? Now let's say along the side you wanted to create trait. So a trait would be something like a trait philosopher, something unrelated to this class hierarchy. Okay, in a trait philosopher, you could say define philosophize colon string. So you can define a trait called philosopher, which has a method called philosophize. You can define a trait called color, and then you can say val color colon string. So you can define these traits. You can define a trait called philosopher. You can define a trait called color. And now you can say class Kermit extends frog with philosopher with color. All right. And you can say, okay, so I've extended frog with philosopher with color. And now you have to say override val color equals green because Kermit is green. And you can say define philosophize string equals, I don't know, I think, and therefore I am. So this is an example of a trait, right? How many traits can you use with a class? As many as you want, right? So you can, you can mix in a lot of traits, but hold on. What did I do here? Let's see, I might have forgotten the syntax for multiple traits. So Scala mix in with multiple traits. Oh, no equal sign. Yes, thank you. Okay, that might have been my mistake. Let's go back here. Oh, of course, no equal sign. It's not a method. Thanks. So this is the syntax. You have to say with philosopher with color. You can mix in as many traits as you want, right? So let's say what are the other traits you have? Let's say trait TV personality. And then val show colon string def tagline colon string equals. So let's define a value show and see, and then I can say with TV personality. And now when I say TV personality, I have to override what? And by here I have to say override, though I think with Scala, you don't have to say override for traits. So I'll explain the difference between mix-in and multiple class inheritance, right? They do something similar in a few ways, but they do some different things as well. So this is important, right? So let me draw some pictures after this and explain the main difference between multiple inheritance and mix-ins, okay? So give me a second. I will explain this in a second. Why just mix-ins? Why not multiple inheritance, right? So I'll tell you what are the similar things and what are the different things. But here's the thing. So I could do override. So I need to do override val show, and I say Sesame Street, right? And then I say override def tagline equals yeah, whatever Kermit says. All right. So this is basically a way you use mix-ins, right? So you have classes that can extend from another class, but you can do mix-ins. And what is the main difference here? So why not multiple inheritance and why mix-in? So let's get to that. Yeah, that's right. Muppets. Sorry, not Sesame Street. I mixed it up. Yeah. Thanks. That's a good point. So let's do this, right? So what is happening here? Why not multiple inheritance? So maybe this was covered in one of the recitations earlier. What is the problem with multiple inheritance? So what is the problem with multiple inheritance? The problem with multiple inheritance is the so-called dreaded diamond, right? So what's the dreaded diamond? So let's have a class A. Let's have B and C inherit from A. And let's do D. So D multiple inherits from B and from C. And let's say, so what is happening here? So if you look at D, if you look at the class D, inside D is a copy of B, and inside D is a copy of C, but inside B is a copy of A, and inside C is a copy of A. So now, unfortunately, you're ending up with two copies of A. You're ending up with two copies of A. So each method of A, each field of A is replicated twice. And the problem is, suppose from inside D, let's say A has a field called X. So inside D, I refer to X. So I say this pointing to X. And this is in C++ typically, right? If I say this pointing to X, which X should I get to? The X that is inherited from B through A, or the X that's inherited from C through A, right? So it's very difficult to say which X do I refer to. There are two different X's, there are two different cells in the memory, and they could have two different values. Okay, so this this diamond pattern in multiple inheritance is a big problem. Okay, so far? So the nice thing about mixin is it's not the same as inheritance. So what is mixin doing? So first of all, in Scala, any class, let's call a class C, can only inherit from one base class A. So these are classes. These are classes. Whereas a trait, it can inherit from a lot of traits, T1, T2, T sub n. The nice thing about a mixin is that it's not as if that C has a copy of T1 inside it. So you don't have a subclass or a copy of T1 inside C. What is done is all the fields of T1, all the fields of T1 are basically placed inside C. So there is indeed an instance of A that lives inside C. So inside C, you can imagine there is an instance of A that lives in there, but there is no instance of T1. Traits do not have instances. So there is no instance of T1. And by the way, if T1 shares a field, let's say I, and Tn shares a field, let's say the same field I, well, there's only going to be one field of that type I. Is that okay? So we could try this, right? Let's try a couple of experiments just to see how mixins are different from classes. Okay, so so the main point here is if you have an integer I here, and if you have an integer I that comes from T sub n, there will only be one copy of that integer I in C. The idea that there is a copy of C I through T1 and a different copy of I through Tn does not happen in Scala. Is that difference clear? This is the key difference between a trait and a mixin. Okay, let's see what happens, right? So Kevin has an excellent question. So what happens if you have a trait and you have two different conflicting types or two different conflicting implementations? So it's the best thing is to try. I haven't tried this in a while, but let's try this. Okay, so let's have trait T1. And inside trait T1, let's define T of type string. Okay, let's have trait T2, and inside T2, let's define T of type int. So here is a conflicting type. Okay, for T. All right, and let's do this. Let's have an abstract class A, and let's do class B extends A with T1 with T2. Let's see what happens. So you cannot do it. Overriding value T in trait T1 of type string and value T in trait T2 of type int has incompatible type. So in a trait, you are not going to allow these things with incompatible type. But if I had a compatible type, no conflict, then I'm perfectly fine doing it. Now, of course, it's going to complain that I haven't defined T. So I will define T. And notice here, I did not need to write override. I only need to write override when I'm actually inheriting something. Okay, in a mixin, when I am mixing it in, I don't need to write override. Though for me, I always write override. Scala will not complain if you write override, but you don't need to because technically you're not overriding because technically you're not inheriting. Okay, and you can do the same thing, right? In an abstract class A, you can define a type T, and it happily allows you to do it, noting that there is only one copy of T ever. There's only one copy of T, even though T comes from 3 different places. Is that good, Kevin? So let me answer the second part, right? So suppose I defined a method foo. X plus 2. And let's say I define the same method foo here in T2. What do you think will happen? Let's see. It's not allowed. Okay, so it says class P inherits from conflicting members, method foo in trait T1 of type int, int. So you can, but on the other hand, let's say I did not define foo here, then you're fine, because it takes this definition of foo and absorbs this definition of foo in here. Okay, so this is very, very subtle. Okay, but the main point about a mixin, there is a very, very important difference between a mixin and inheritance. Okay, in inheritance, you actually will have, even though it's not clear, you will have a copy of that base class inside the abstract class, whereas here you won't have a copy of that trait. Okay, so that is very, very important. It is very important to understand that you don't have a copy of a trait and so on. Okay, now why are traits useful? Why is mixin useful? Well, traits are useful for a lot of reasons. Okay, and one of the main reasons a trait is useful is, for example, I could define useful traits like this. So one of the most useful traits is something called an ordered trait, and it simply says, define a method called compare. So let me. This becomes more useful when I do generics in a second, but bear with me. So suppose I define a method called compare, and compare, let's say, equals 0 if two objects are equal, greater than 0 if x is greater than y, and less than 0 if x is less than y. So suppose I somehow provide a comparison operator for you. Just to be more interesting, let's do a string comparison, because number comparison is not difficult at all. So suppose I did a string compare operator where I compare two strings, and it returns a number which is 0 if the numbers are the same, positive if the first number is greater than the second, negative if otherwise not. Now, in using a trait, I can now define overloaded operators. So I can do operator overloading, and I can now define all the other operators, and I can say, oh, equal to is in terms of compare, and so on. So I can now define all the operators. I can overload the equal to operator. I can overload the less than operator. Okay. So I can overload all the operators, and conveniently the user never needs to do that. The user just mixes in this trait, and then the user has the benefit that all these overloaded operators are in their class. So, right. So I can do all these overloaded operators. I can write my sorting function with my comparison operators. So I can give you a sort function which takes in a list of strings and returns a list of strings. So this is very, very useful in defining these kinds of things. So you give me a comparison operator, and I will overload all the other operators for you based on the comparison operator. And I will write a sort function, so I can implement quicksort and so on. So this is super useful, because if you changing a comparison operator is just a matter of implementing this function differently, and then you would have a different way of doing it. Okay, so this is important, right? So this is one way that traits are commonly used, where you bundle a bunch of useful functionalities together. And this is not done through inheritance, it's done through mixin. Okay, everyone understand at least like why a trait is useful, and where you would use a trait? Okay, because it's very, very important, right? So now once I have this ordered operator, I can do various things. Okay, now interestingly enough, what is happening here? Yeah, so this will become clear later. Equal to cannot be written like this, so I cannot say equal to let me just say equals greater than. I can't overload this operator just yet. I will show you how to overload this operator in a second. I need traits for that. I need generics for that. I can't overload it that easily. So right now I can just write things like this. But the main power of traits comes when you add it with generics. So I'm going to talk about the next topic, which is the topic of generics. Okay, so we've already seen generics before. So we've already seen generics where we have been writing functions like this. So we've written functions like this already, right? So the idea here is let's define a function called foo, which takes in a type parameter t. So type parameter t. And it says it takes in an argument x of type t, f of type t arrow t, and returns something of type t. And I can say, foo string of hello. And I can say function x colon string to x dot reverse. So I can do something like this, right? So this is the function and t here is string. I don't even have to write string because many a times Scala just infers that it's foo of string. So these are called generic functions. And the reason they are generic is you can plug in any type t here. So I can say foo of 25, and I can say x arrow x times x. Hold on. What's wrong here? Oh, I have to say x colon int. Okay, so I can do all of these things, right? I can use the same function in with multiple types, and this is actually calling foo of int. And we have done this for CPS, right? This has already been something we have looked at. Okay, so far. But we can do the same thing for classes. So we can actually write generic classes and generic types. So how do we do that? So we can write a class like this. So class, a list or linked list of t. And this is a way to say we can define a linked list class where t is going to be the type of the object node. Okay, so or I can say my list because Scala already has a linked list, so I don't want to redo this. But you can create something like this: class my list of t, where t is a generic type. So t is a generic type, and you can say things like this, right? You can say define val lst colon list of t equals nil, and you can say add define add element to list. Element is of type t, and it returns my list of t, and you can say elt colon colon. So you can say let me do it properly. Okay, so let me make list as a type parameter. All right, and now I can say add list. I can say new my list of element colon colon lst. So I can do things like this, right? Define pop push element I can write these functions. So what am I doing here? So I'm just saying I can define pop element or isempty. I can say list.length greater than 0 or less than equal to 0. So I can define all these functions, and this is all generic. And the reason it's generic is I haven't committed to what kind of an element lives in my list. All I have said is this works for any list or any type T that I care to plug in here. And this class works. So for example, I could say val m1 equals new my list of int. And I could say nil. And I could say val m2 is m1 dot push element 55, val M3 is M1 dot push element. 43, M3 dot is empty. So I can do all of these things. And the nice thing is I can define a mylist of int, and I can use the same thing to do a mylist of strings. So S1 is new mylist of string, and I can say nil, and I can say val S2 is S1 dot push element hello, val S3 is S1 dot push element, or S2 dot push element world, S3 dot is empty. So I can operate on it, and now I have created a list of strings. So this is very, very useful for data structures. If you have data structures in Scala, most of them are generic. So for example, the Scala list is a generic data type. So in the Scala, the list data type is a generic. So you have list of int, list of string, and so on. So generics are super useful in Scala. All right. And the way to make a generic is to add the type of the type parameter within square brackets. All right. And then you can use T everywhere. And wherever you use T, it stands for this type, T. If you have done templates in C++, then you know exactly what I'm talking about. So in C++, you do have the notion of templates, except in C++, you would use angular brackets, whereas in Scala, you use square brackets. But that's really what T does in Scala. Everyone okay with this idea so far? Everyone okay with the idea of generics? All right. So if that's okay, then let us talk about why do you use generics and how do you get things done with generics? All right. So maybe I will just go ahead and reuse some of the examples from my notes. Okay. And most of these examples are already in the notes. And this T is called a type parameter. Okay. And so you can write classes like this. So you can write an abstract class T, and you can have methods, you can have arguments and field members, which all depend on this type parameter T. All right. So you can use it in various ways. But now let me talk about some kind of different ways of using it. So here let me do a different thing. So let's say I wanted to do some data structure. So I wanted to do class myContainer of T. Okay. And let's say in myContainer, I wanted to do a transform method. And so let's say myContainer has within it a list, which is a list of type T. Okay. Let's say I wanted to do transform, a method called transform. And in transform, what I wanted to do was, if you gave me if I wanted to do the following, I wanted to take a list of T. So I wanted to say list dot map T arrow T dot transform, or something like that. Let me make it even simpler. Let's just do a single element here of type T. And in transform, I just wanted to call element dot transform. Okay, something like this. So this is a very, very simple class. I'm not going to keep a list. I'll just keep a single element, ELT of type T. And I have a method called transform. And when I call transform, I want to call ELT.transform. Okay. Do you think this will work? No. Why won't it work? Tell me. Okay, you don't know what ELT is. All right. Okay, so no, those are not the, I mean, it won't work, but those are not the right reasons why it won't work. The problem here is this: we don't know what T is, right? So we do not know what T is. But we would like to like T to have a method or a field called transform. Okay, and let's say transform returns an integer. So we would like to have T to have a method called transform that should return an integer. Okay, so the point here is this: you can do things like this, but the problem is you can't plug in any kind of capital T here. You can only plug in those kinds of capital T that support a method called transform. Okay, so if I try to run it, it's not going to work because it says value transform is not a member of the type parameter T. Is that okay? So do you see the reason why it doesn't work? So often I have to write code where I have a generic, okay, I have a type parameter, but I would like to use type parameters which are somehow constrained in certain ways, and constrained in ways where let's say I want use generics where I know that the generic type that you're plugging in has a method in it called transform. Okay, now if I needed to assure myself of that, how would I do this? So I would do it something like this. So I would say trait transformable, and I would say, let me define a function called transform. Okay, and let me put in a type parameter T, and let me put in have a method called transform, which takes in an argument of type T and returns a number. Okay, so now that I have this trait transformable of T, here's what I would do in my class. So I would rewrite my class like this. I would say, let me call my container with T, but let me use this symbol, and I'll explain what this symbol means in a second. And then I would say T is less than transformable of T. Okay, and so once I do that, you will see, hold on. Oh, okay, sorry, I don't need this. All right. So in fact, let me simplify this. I'll get to this more complicated thing. Let's just do it this way. So I have something called transformable, which has a function called transform with integer, and that should work. All right. So here, what am I doing is I'm saying T is less than transformable, which means that if you have a class hierarchy, what you're saying is that the only kind of type parameters that are allowed, so you have transformable. I want T to be either extends or mixed in to a trait transformable. All right. And this is what the less than colon constraint means, that I will only allow those parameters T to be plugged in, where T is somehow deriving either through a mix-in or through an inheritance from the trait transformable. All right. If I have that, then it works, because what happens then is you are assured that anything that inherits or extends from transformable has inside it a method called transform. So when I call element.transform, I am assured that things will be fine. Is that okay? Everyone okay with this so far? Okay, so you can do some cool things with this, right? So you can say, let me define a trait called ordering, and let me have a generic parameter called T, and this says I am defining an ordering on type parameter capital T. And now I can say something like this. I can say, for example, I can say define compare T Okay, so let me define a compare method. And now I can say some cool things, right? So what can I say? So let me show you. Actually, I have this code written. And you know, the TAs will actually show you a little bit more about this today. But you can say, okay, I can define a trait called ordering, and I can define a compare operator on it. And compare operator defines +1 if you know, this object is greater than O, -1 if this object is less than O, or equals if they are 0. And now I can define a binary search tree, and I can say a node of a binary search tree is a class T which is somehow less than or equal to, or less than or colon, this ordering trait. And what that means is I am going to require the class to have a compare method inside it. Okay, so so I can do those kinds of things. Yes, Ebenezer, the exam is today, but you can take it at your own time. So I'm not going to you know, have it in the class. It's there until tomorrow at 5. Okay, so you can take it until tomorrow at 5. So the nice thing about ordering is I can define these kinds of operators. So I can define a less than equal to operator, and I can define a greater than equal to operator, or an equality operator. So the nice thing about these traits is I can define this operator. Hold on. I shouldn't call it EQ. I should call it my equals or something like that, because EQ has a different meaning in Scala. I'll explain that in a bit. But so you can define a trait called ordering, and now you can say you know, class my number extends. I can say extends ordering on my number. Okay, which means that I'm now committed to writing a function called less than or equal to T1 colon my number. Okay, and so let me write give a number here, val j colon int, and I can say this dot j less than equal to T1 dot j. So I can say Boolean. And the idea here is when I extend to ordering of my number, then these two methods will have to be implemented. And capital T is my number, so this replaces my number. This is replaced by my number. Is this clear? It looks a little bit strange and even scary, but all this is saying is when I define this class or my number, and I extend ordering of my number, which means that these two have to be mixed in. The less than equal to and the equals method have to be mixed in, and they have to be mixed in with this capital T being my number. So when the capital T is just my number, then you have to mix in the less than equal to by substituting capital T with my number, which becomes this method. And here you have to have the my equals method with this capital T substituted by my number. Okay, so these are like standard ways in which we use generics and traits in Scala. Okay, and you can override operators. So you can say define less than equal to. So you can override operators. You can do all kinds of crazy things. Something like that. So you can define strictly less than, right? So these are useful things you can do where the user doesn't have to do this every single time. As long as you just define less than equal to and equal to, the user, you can take care of everything. Or you don't even need equality, because equality can be defined if you have less than equal to. So these are ways by which you can make things convenient for the user and avoid writing code, the same code again and again and again. Is that okay? And so now you can say class, binary search tree, and you want whatever the element type or the key type is, you can say that has to be less than or equal to ordering of key. And this is a way of specifying that you are only allowed to use those kinds of keys for a binary search tree for which these methods are defined. So you have to mix in or inherit from ordering. If you don't mix in and inherit from ordering, then that key is disallowed. Is that okay? So this is a very nice way of designing data structures, because what you want to do is you want to write one binary search tree implementation, and you want the same implementation to work for a key with a string, or a key being an integer, or a key being a double precision, as long as I know I have a comparison operator. I have a less than equal to, or a less than, or a greater than, So as long as I have comparison operators, I am fine. And so what you're specifying here is that whatever you use as the key better inherit from this ordering trait. So for example, my number can be used as a key for a binary search tree under this definition. So is this type constraint clear? When I use generics, if I have type constraints like this, is the meaning of the type constraint clear? Okay, so let me try and walk you through another example, maybe a simpler example that's not a binary search tree. Okay, so in my notes, I have a simpler example. So let me try and do this simpler example right now. Okay, so and this is based on a very nice blog post that I found that explained type bounds or type constraints very nicely. Okay, so let me define at the root of everything. Let me define some a trait called thing, and thing has a member called name. All right, up top I will define this, and then let me define a trait called vehicle, which extends thing. Okay, so vehicle is a trait that extends thing, and car is a type of vehicle. So these kinds of definitions are sometimes called ontologies. Okay, so these are sometimes called ontologies. Um, and these are very, very common in object-oriented programming. Uh, People do, in software engineering, will create these detailed ontologies. All right. So now I define a class car that extends vehicle. Okay, and I have the name as a class parameter, and I've defined a function called get name. All right. And likewise, I define a class bus. A bus extends vehicle because a bus is a type of vehicle. All right. Um, Now let me define something called a sedan, which extends car because a sedan is a type of a car. Okay, and so on. So and I have a big car which extends sedan. Uh, I have a Jeep which extends big car. I have a motorcycle which extends vehicle, and I have a tomato which extends thing. All right. So what does my class hierarchy look like then? So at the top there is thing, and then from thing I have vehicle, from vehicle I have car, from vehicle I have bus, from car I have sedan, big car, Jeep, motorcycle, and then from thing I have tomato. All right. I can make a drawing, a diagram, but let's keep going, and if needed, I'll make a diagram. All right. So let me now define a function called uh, park vehicle, and I want to create a function called park vehicle, and I want to say, it will just print that I parked the vehicle, and it will print the name of the vehicle that I parked. Okay, so this is the idea, but obviously this is not working. Why is this function not working? Can you explain why this function is not working? You can read the error message, it says there, but can you explain why this function is not working? Remember, capital A is generic and small a is of type capital A. Anyone? So we didn't specify A to be of type thing, right? That is number one. Or even more generally, who tells you that A has a field called name in it, right? Uh, I am expecting A to be as yes. I am expecting A to have a type field, but have a field called name, but it doesn't have that. So what I should do is exactly that, right? Exactly what Jacob suggested. I should make sure that A inherits from or is below thing or mixes in things in the class hierarchy, and then this is perfectly fine. Okay, so this is perfectly fine as long as A is below thing, because as long as A mixes in thing, it's bound to have something called name, because thing has something called name. So this is perfectly fine. All right. So I can park a vehicle, I can park a sedan, right? So I can park any object that mixes in or inherits from thing. So remember, and thing is at the very top of this class hierarchy. So all of these objects can be parked. But that means that I can park a tomato, right? Uh, and I don't know if you have ever parked a tomato, but that's not acceptable. Most people who are into this parking lot business don't like to park tomatoes. Okay, uh, is this okay? So because I haven't restricted us from parking anything that can be less than thing in the class hierarchy. Is this okay? So that then I can park a tomato, I can park my school bus, and how would you like to have a school bus taking like 3 or 4 spots in your busy parking lot by your local King Soopers, right? You don't want a school bus parked there. That's definitely no place for a school bus, right? So you don't want to park a school bus either. Okay, so I could fix this, right? So I could say, well, I don't want to park a tomato, so I can say maybe the correct constraint for the park vehicle is that A must be less than a car. So if it's less than a car, then I can park a vehicle, but I can't park I can park any kind of sedan, but I can't park a school bus because a school bus is not inheriting from a car. So if you go back to it, a bus inherits from a vehicle, a car inherits from a vehicle, and a bus inherits from a vehicle. So it's perfectly fine for me to say this A less than car, and therefore I fix the problem that I can no longer park a school bus or I can no longer park a tomato. Is that okay? With this constraint, A less than car. Okay. Now, what happens though is, let's say let's say I don't want to allow you to park something like a Jeep. All right. So let's say anything I park, uh, you know, cannot be a Jeep. All right. I cannot park a Jeep. So then I can write the similar constraint, but I can write a greater than or equal to constraint. So I can say this A is greater than or equal to big car, and A is less than or equal to car. And this allows me to specify in the class hierarchy exactly in what range can this type parameter be. So I can say A greater than or equal to big car, and this has to be read A less than or equal to car. So this applies to this generic type parameter, and you can have slightly more complicated constraints like this. And now you cannot park a Jeep because a Jeep is below a big car in the class hierarchy. Is that okay so far? So type constraints are very useful. And the reason type constraints are useful is when you have generics, it constrains the generics to be between some lower range and some upper range. All right. So let me just clarify any questions that you may have about these kinds of type constraints and generics. Uh, I think in the recitation, the TAs will walk you through how to actually build a data structure. I think they are doing part of a binary search tree data structure, and show you how you can use the object oriented features to build that data structure properly. All right. Since no one has any questions, do people have questions? Because I'm done with my lecture like 8 minutes early because no one stopped me with any questions so far. Any questions so far? Okay. So if there are no questions so far, then I'm going to end a little bit early. You can use the remaining time to take the exam if you wish. Or if you have further questions, you can stay back or I can help students. I know some students had questions about CPS, so I'm happy to help you about CPS. So all right, so stick around if you have questions. Otherwise, see you on Tuesday. Thanks.